Yeah, I was just about to say, this one's also in the book, and these slides I think were also made up during an online Zoom class, and we can take advantage of them. All right. So, what's the knapsack problem? Is you have a knapsack and a bunch of objects, right? And so the input tells you about tells you the volume of the entire knapsack, and it tells you the volume of each of your objects and the price of each object, right? And what is a solution? A solution is valid if let's S be the set of things in the solution that you take. If you sum up the volumes of the things you take, then it fits in the knapsack. All right. So we're not doing any weird packing. It's all fluid, kind of, right? And then what's the cost of the solution? Is you sum up everything you put in the knapsack of the price of the object, right? And that's the value that you're running out of the store with, right? Does that make sense? So that's called knapsack. Get as much value in your knapsack as possible. No, you're a robber. All right, so you've broken into the store and you want to fill the knapsack with as many diamonds as possible. Right? All right, so we can say here are various objects. Which do we put in our knapsack first? We want a greedy criteria, right? Remember, each object has a volume and has a price. All right. So which object do we put in the knapsack first? The smallest. All right. Oops. How about most valuable? All right. Is that an optimal solution? Exactly. Because the problem with, I think I'm giving a sort of this thing that's the most valuable, it might be huge, right? And it fills up your whole knapsack. That's not very good. So here the most valuable is that, but you can't put anything else in the knapsack, right? So you are better off putting two things in the knapsack, right? So the other option, and the same with putting the smallest thing, right? It might not be worth anything, right? So what we want is bang for our buck, right? Actually, not bang for a buck. We want price for our volume, right? You can think about each cubic centimeter of knapsack. We want as much value than is possible, right? And here's the problem that this doesn't work either, right? So in this, you'll see this is the price 5 divided by 7, it's less than 1, right? But these are all 1. So you put one of those in, and now you can't put anybody else in, right? Right, because we only have 3 room left. So you can't put in a bear of size 4 or a wagon of size 7. Yeah. Yeah, well, that's our exactly. So our question is this does this greedy algorithm give the optimal solution? And the answer is it doesn't, right? And it doesn't because here this is giving us this most price per volume, but it doesn't fill up that much of the knapsack. But we can't put anything else in, right? So we switch over to optimal is you just put the wagon in and it's better, right? So it turns out that this problem is NP complete. So it's there's no polytime algorithm for solving it, even though we will come up with a dynamic programming algorithm, and we'll talk about tiny time again. But anyway, there's all right. So we are going to do something that works here, right? Let's go back to this. Can you tell me how we could fill in the knapsack with more value? Yeah, but that's the problem. How do you find that combination? Right? Combination. Yeah, but there's an exponential number of combinations, right? There's an exponential number of subsets. And so trying them all takes an exponential amount of time, right? So here is what I'm going to suggest. Yeah, but that's the greedy algorithm. You know, we tried sorting them by volume, we tried sorting them by price, we tried sorting them by price per volume, and we saw that none of those worked, right? So the truth is, if you're trying to solve this problem, if you could solve it, you could break all cryptography and be rich. And we, you know, so don't, you know, feel free to think about it, but don't get too excited here, right? So in order to solve it, we need to change the problem, right? And we're going to change the problem by cutting the bear in half. It's very sad, isn't it? You know, Solomon did something like that with the baby. So, well, here in this problem, think about our objects being more like a fluid, where you can, if you put in half of an object, you get half of the price, right? So here, we're putting in 3/4 of the bear. So it gives us 3/4 of the price, which gives us a bigger value, right? And it becomes optimal, right? So this problem is now, it's the difference between integer solutions and non-integer solutions, right? Are you allowed to put in half of a bear, right? So if, in general, if you're allowed to put in non-integer solutions, then the problems become much easier, right? We studied network flow, but that's an example of, in fact, we should make sure we talk about that. One of the things I forgot, I didn't talk about when we were doing network flows is a broader class than network flows is called linear programming. And nobody in computer science should graduate without knowing what linear programming is. We certainly will not give an algorithm for it because it's hard, but we should state what the problem is. So remind me to do that on Monday. And so all of these non-integer problems can be solved by linear programming. All right, so now our algorithm is sort them by price per volume, and you go through them in that order, and you put in as much as you can. In fact, you're going to be putting all of it in until the last one, where you put in as much as fills it up, right? So it'll be integer except for the last guy gets cut. So that's our algorithm. That's a greedy algorithm. And we're going to prove that it gives you the optimal solution, right? Well, we have the blocks were worth 4, and the entire bear was worth 4, but we only took 3/4 of the bear. So we got 3/4 of the 4. That gives us a 7. No, the wagon was only 5. It had volume 7, right? But its price was 5. So how are we going to do this? We're going to get rid of this thing up here that's bugging us. That was probably hit the wrong one. That one. And this will be good until we hit the escape button. So, all right. So we're not really sure what these pictures are going to have up here, but because again, they were made during a class. But we're playing the game, right? So what AT-1 is the red thing is the knapsack, and you can see we put in J1, J2 up to T-1 in the first T-1 steps, right? And then I don't know why this is over here and not over here more, but right, AT will slide that object in, some object in. And what object is it taking? It's taking, of the objects that haven't been taken yet, it's taking the one with the highest price per volume, right? Everybody good with that? So let's just bring this in and see how we like it. All right, so again, here we have AT-1. Here's ST-1. It has some other objects here that we don't know what they are, right? And then AT slides in this object here. This is a better picture, right? And then how do we make ST? Well, we say, fairy godmother, you gotta keep the first T-1, right? So she keeps those. You have to take the JT, so she takes it. And what do we get her to delete? Anything that's in the same spot in the knapsack, right? Now, you might argue that the fairy godmother doesn't actually tell you the order she put them in. She just tells you which ones she put in, right? We might not know the order here. So I'll say order them arbitrarily, right? Doesn't matter to me. Order what she took arbitrarily. Then if it's in the same place in the knapsack, right, then delete it, right? Does that make sense? Yeah. Well, it's because how much, this is the volume, the distance from here to here is the volume of JT, right? This distance is the sum of the volume of J1, J2, right? So that's the volume. We're thinking about volume is along a line, right? And so if she took the same ones in the same order, then these 2 points are the same, and we just take, this has volume, some volume, and we just keep throwing things out until we throw out. In fact, I'm willing to say, fairy godmother, throw out anything you want that the algorithm hasn't had so far of total volume that we're putting in, right? In fact, I don't even care which ones you're throwing out. She could throw out a little bit of this and a little bit of that, right? she throws out equal volume, right? Does that make sense? All right, so now, oh, and here it says we're keeping part of it. All right, so now this is our new ST. And what do we have to show? We have to show it's consistent with the algorithm. Well, we made sure we didn't throw this out. We put this one in. It's consistent with the algorithm, right? Is it valid? What does valid mean? Yeah, you're getting on the price. Just valid means that it adds up to the volume of the knapsack, right? Right. And we were very careful. We put in the volume of object T, and we told her to throw out anything of the same volume, right? So we know what she has is of the right volume. And so now what's remaining that we have to check? The price, right? We want to show that the price of ST is at least the price of ST minus 1, right? The total, it's the sum of the prices of these things. And if you took only part of K3, then you get the proportional part of the price. Right? You got an Looks like an No, do you know how to calculate the price of ST? And if you only took part of it, then you get that part of that price, right? So that's the price of S3 of ST. Similarly, we can ask the price of ST minus 1. And all we're asking is that the price of ST is greater or equal to the price of ST minus 1, right? I mean, we just have to show that the prover provides this thing whose price is at least as good, right? So how do we do that? You have a question? So it's price per volume that we're looking at, and whenever they're ties, we do it arbitrarily. No, I'm going to say that if she takes a different object, it's different. So you have to swap, right? Just like we did with the quarters, right? All right. So anybody want to argue to me that this price is good? Kind of hard. So let's look at what is it that we. So first off, the job Ks are future jobs, right? They're not the jobs that we've taken so far. So what do we know about K1 versus JT? What do we know about their differences? Yeah, we do, because the algorithm could the algorithm have taken K1? Right, the algorithm took up to here. Then there are a bunch of jobs remaining. It did take JT, so it could have, right? It could have, it did, it could have. Could it have taken K1? It could have, right? Because it's a job it hasn't considered yet. But it didn't. Right? It could have, but it didn't. Why didn't it? No. Price per volume is lower. Price per volume is lower, right? So why do I have a little square here? The volume of that square is 1, right? The unit. So I'm asking what's the price of that much of K1, right? And we're comparing it to a little square, the same size square of JT, right? Price per volume, this price per volume is bigger than that price per volume, right? And so when we're switching from ST minus 1 to ST, why don't we do it to make the switch one little square at a time, right? Let's just first switch this little square from being K1 to being JT. Was that an improvement? Yeah, because that little square was worth at least as much, if not more, right? So that was an improvement. And then we do the next square and the next square. We do all the little squares. Each square is an improvement, right? So we can't go wrong. And that's the entire proof. So yeah, I was saying you do it a square at a time, right? We replace that with square with that square with that square, right? And each is an improvement. You're trying to do it all at once. And I'm saying, yes, well, we're placing this much volume with some volume of J1, and that's going to be an improvement, right? Does that make sense? It's just the math is a little harder, right? Right, everybody good with that? And I think it is separating out the loop invariant stuff. I was making every time people have to go through the whole loop invariant discussion, and you know, you should have that in your brain, but really what we're focused on is this game. Everybody understand the game?